Hello, everybody. In part one of this lecture, we talk about how we can model the vibration of a bar, in particular, the longitudinal vibration of a bar. And we managed to find the equation that govern the longitudinal vibration of a bar. So to recall and refresh your memory, we have a bar, we set up our coordinate x. This bar has density rho, a modulo of elasticity E, cross-section is A. Any point along this bar, let's call that point at a specific distance x from the left side, uxt is the vibration of that particular point, which governed by this wave equation. To solve this one, a classic method is method of separation of variables, meaning we assume the response uxt composed of two parts or two functions, ux and tt, which tt can be any harmonic function like cosine omega t or sine omega t, or combination of them like cosine omega t plus sine omega t. So let's substitute my uxt. I guess a function, and I assume my response uxt can be ux. For simplicity, let's for now assume cosine omega t. All right. So if I find the second derivative of u with time, it's going to be minus omega squared cosine omega t multiplied by ux. And if find second derivative of u with respect to x is going to be derivative of u with x squared multiplied by cosine omega t. Keep in mind, since now ux is a function that its variable is only x, I just use the regular derivative rather than partial derivative that we do here. If I substitute these values into my equation, I have minus omega squared cosine omega t u. I just simply write u is equal to c squared, and here I have second derivative of u, that's the uppercase u, dx squared cosine omega t. I can get rid of this cosine omega t, rewrite my equation. I ended up second derivative of u, x squared, omega divided by c squared, u equal to 0. So as you see, we managed to separate our variables. Initially, our u, the response was function of x and t, but here we have actually a function or a regular differential equation. The solution for that one, again, I can guess a solution, ux, which we solved this sort of problem before, is sine lambda x plus b cosine lambda x. It's a typical answer for this system. Now, if I substitute that equation, to do so, I need the second derivative of u with respect to x. That will be a lambda squared sine lambda x minus b lambda squared cosine lambda x. If we substitute this value into that equation, we are going to end up with minus lambda squared omega c squared a sine lambda x plus b cosine lambda x. I just skipped some algebra here. Please try it. Substitute this value. You have derivative of u, second derivative of u with x, and you have ux. Substitute these parameters here, simplify it, you are going to end up with this term. This equation is correct if lambda minus lambda squared plus omega over c squared is equal to 0, and it gives me lambda equal to omega c. So we managed to find the value of lambda. Let's make all of these a little bit more compact. So now I substitute that value into ux. Ux is equal to a sine omega xc plus b cosine omega x. So that's cosine omega xc. Right, we managed to find ux, which is the shape of vibration. So this is the shape of vibration. Right? Now this ux, of course, depends on the boundary conditions, may have different form. Let's just try for a simple cantilever system. So for this cantilever system, obviously, at the point over here, when x is 0, u also is 0. If I substitute this value into my u0 is going to be a sine 0 plus b cosine 0. I ended up with b equal to 0. And my second boundary conditions is at the free end. So free end. As we say it's free, it means there is no force there. Previously, we learned that P can be defined as AE derivative of U with X. If you don't know how we get there, please check the previous lecture, which also is posted on YouTube and on Canvas as well. So this value is equal to 0. From here, I conclude that du dx is 0. We have the function ux, so du dx then is going to be a omega c cosine omega x divided by c. Right? So keep in mind, this is du dx. Over here, we managed to find our function ux, and we already know b is equal to 0, so we don't care about that part. When x is equal to L, we know dux dl is 0, so it means omega c cosine omega L divided by c is equal to 0. Therefore, omega L divided by c can be pi over 2. It can be 3 pi over 2. It can be 5 pi over 2. An infinite answer for that part. I can compact them and write everything in maybe a better form and say perhaps n minus pi. All right, we can test it. If I substitute n equal to 1, it gives me pi over 2. If I substitute n equal to 2, it gives me 3 pi over 2 and so on. So n can be 1, 2, and so on. All right. So from here then, simply I can write down omega as n minus pi and divided by LC, and I can substitute C. So n minus 1 over 2 L, and of course we have pi here, E over rho. Remember C, we define C as C squared as E divided by rho. Now here, I'd better call this one omega n and say n can be 1, 2, 3, and infinite. It means my system has infinite number of natural frequency, right? So, and similarly, we can find the mode shapes. Let's again do a little bit of compacting here. So at that free end, we have that scenario. At that end, we have that scenario there. Can I substitute it there? Okay, I'm just gonna write it as that. And here was our final conclusion. Nice and clean, we managed to find the natural frequency. So as for our mode shapes, ux is going to be equal to a sine omega xc, right? Remember, this is the general form, but we proved that b is 0, so I ended up with that. I can then simplify that one as ux equal to a sine. I just substitute omega over c by that value. So it will be then n minus 1 over 2 pi divided by Lx. All right. Here is our mode shape. And again, we put n. We have a system with n natural frequency and n mode shapes. We can test few of them. Let's just here, let's check the first few modes. If n is equal to 1, omega 1 will be 1 minus half pi divided by L E divided by rho. And it gives me 1.57 L E divided by rho. Actually, we can check it with the value that we found before. Check with n degrees of freedom. Remember, in previous lecture, we said, what if we model this system as a 1 degrees of freedom system? We said if we model it as 1 degrees of freedom system, we will find the natural frequency to be 1 over L E divided by rho. And then we said, what if we go a little bit with a more complex model and 2 degrees of freedom, and we find the first natural frequency to be 1,236 L E rho. And we continue with 3 degrees of freedom. And we find the first natural frequency as E divided by rho. And I task you to check the 4 degrees of freedom. I hope you did that. If you do that one, perhaps you're going to get that number. And so on. So you can go with more degrees of freedom. So as you notice, as we go with higher and higher degrees of freedom, this number over there, the rest are the same, is getting very close to what we have for the continuous system, which is the actual value, the real value. All right. Perhaps if you go with 100 degrees of freedom, maybe you get very close to that value. And we can find U1x, the first mode. So we have our general formula over here, there. I just substitute n with 1. So I'm going to get a sine pi 2Lx. So that's my first mode. That's the shape of first mode and first natural frequency. Let's just put them inside a box. Let's try n equal to 2. And if n is equal to 2, omega 1 will be 2 minus 2 pi L E divided by rho. And it gives me pi L E divided by rho. Of course, you can substitute that value to get the actual, and U2x, the second mode, will be a sine 3 pi 2Lx. All right, and we can, of course, continue to find higher natural frequency and higher modes. Let's just quickly plot these two modes and see how they looks like, right? So here I have my my beam, and I wish to draw my first mode, which is U1x. All right, U1x is a sine pi 2Lx. And here I wish to plot my U2x, which is a sine 3 pi 2Lx. Okay, so let's look at this function. We know if we put x equal to 0, u will be 0. That's easy. Length of this thing is L. If I put L, so I'm going to get a value A. Let's just, for simplicity, pretend A is equal to unit 1, right? And if x is equal to 0, we know u will be 0. X equal to L, u will be equal to 1. Let's try x equal to 2L. Then u will be actually, if I put 2L, will be actually equal to 0. X equal to 3L, x will be minus, u will be minus 1. And eventually x equal to 4L, u will be equal to 0. You see where I'm going with that? I wanted just to draw the complete picture of a sine for you. So we said it is 0 over there, and it is minus 1 over there. So now if I try and I do my best to create a very nice, actually, sine wave for you. Here you got your sine wave, all right? So this is a sine wave. However, we know that, so I'm just gonna do a dot now. So I can, rather than a solid line. So, okay. All right. So this is actually the function x. Imagine if x continue all the way up to here. But for this system, our mode shapes actually is just this first portion of these actually sine. So this is my first mode. All right, so this is mode 1. Remember, this is not the lateral vibration of the bar. This is the longitudinal vibration of the bar. It shows that at any point, let's say at the tip of these bar, how much it vibrates, go back and forth. At the tail of this, because it's fixed, of course, there is no motion. We can try the second one. So if I put x equal, similarly, if I put x equal to 0, I'll get u equal to 0. If I put x equal to L over 3, or maybe 2L over 3, then I get u equal to 0. And what about if I put x equal to L, I get u minus 1, right? And yeah, so if I put x equal to maybe L plus L3 for L3, then I get u equal to 0. Let's just make sure that value is correct. Yeah, it seems it's correct. All right. So similar to that one, then we managed to find that over here I'm going to be 0, and here I'm going to be minus 1, and here I'm going to be 0. So as you see, we don't need to draw an exact actually sine wave. The goal here is just making sure we get approximately the shape of a sine, like this one, right? And it's a good idea also to test. I forgot to write it here. Maybe just move that one a little bit there. Also, why not try x equal to L over 3, which gives you u equal to 1. So that's your 1 unit. L over 3, yeah, it gives you 1. And perhaps you can do a nicer graph here. More realistic again. Let's pretend it is more like a sine wave. All right, so all I did, I graph actually that function. Now my mode shapes, then I need just a portion that belong to this bar. Which is this function there. All right. So we managed to draw our mode shapes here. And again, I emphasize these mode shapes. See, this is one here, this is one here, this is one here, and this is a node. This is just a graphical representation of how longitudinally each point of these bar is going to move, right? So it does not show the lateral deflection. Perhaps I can show you here. Maybe if I stop sharing. All right. So see, I have a bar here, right? Hope you can see it. I have a bar here. Now this bar, obviously, if I excite it laterally like that one, maybe I just, you cannot see it. Perhaps if I hit it, let's say like that one. So it's actually vibrating laterally. Hopefully you could see it. So that's the lateral vibration, right? So what we are interested is in longitudinal vibration, meaning the vibration in that direction, okay? Of course, if I apply a load, let's say if I apply a friction here, I won't be able to see the vibration because the vibration for a bar is in molecule level. We cannot see it similar to the lateral vibration, but it is there. However, we may be able to hear it. Let me try, see if I can do a quick test for you. If I try to just maybe perhaps I apply load to it, more like a friction. Try again. Hopefully now you can hear it. So I try again. See the vibration, we cannot see it, but we can actually hear it. Let's just do a quick test together. Maybe if I play these sound analyzer. So the sound analyzer, I guess I need to, sorry, I need to share my screen. Otherwise, I'm just talking for myself. Share. So the screen is shared now. And yes. So this is a sound analyzer. If I play it, the bottom graph shows the time domain and the top graph shows the frequency domain. You can actually download this one just on Google, search for sound analyzer. You can find something similar to that one. So I can try different sound, and on the top graph you see the FFT of it, for example. So when I whistle, saw that frequency. Now, let's just quickly try together and try to see if we can excite these things again. So you notice there was a frequency of 1.4 or 1.41 which stick out. Let's just try one more time. Yes, here I have a lot of other sound in my office. Yeah, so 1.41 is the frequency. We ignore the first peak because, again, most likely there are the sound of this fan in my office, other sound that it pick it. This is a frequency we can hear it. So in other words, let's go back to our notes. We cannot see the the longitudinal vibration of a bar, but we should be able to hear it similar to what I played. All right, and that actually can be very useful. For example, let's say or let me just go to the next page. Example, if we know the density of the bar, which actually we know this bar is aluminum 6061 and its density is 2700 kilogram meter cube. By knowing first frequency, we can estimate its modulo of elasticity. Let's try. So the formula for omega, the first natural frequency was E divided by rho And keep in mind, this is in radian per second, but the graph that I showed you here, that value is in hertz, and it is 1.41. Therefore, I would say 2 IF1, 1.57 L E divided by rho. So this is the value we found, kilohertz to hertz. Now it is in hertz, 1.57. And I'm going to estimate the length of the bar actually, because keep in mind, I hold it from here. So the distance from here to here, roughly we can say 1 meter or 0.9. Again, this is an estimation, but we can do better. But you got the idea. E and 27. If we do the math, we are going to find the value of E, 69 gigapascal. Okay. Again, you can test it, and perhaps you're going to find a better value for this. All right. Keep in mind, we can have a beam with actually different boundary conditions. For example, we can have a rod. Sorry, I said beam. A rod, let's say a cantilever rod, that other side is attached to a spring, actually, for stiffness K. All right? We can have the same bar a cantilever bar. This time, why not we say we attach a mass actually. Let's say a mass M to that side. Or we can have the first actually bar, but this time to have a free end like that. And remember, in all of these, we are interested in longitudinal vibration of the system, like how this bar moves in that X direction, move in that X direction, it moves in that X direction. So we don't care about the lateral vibration, just the longitudinal vibration of this system. Please try to solve this problem. Use the boundary conditions that you learn in this course. And in next video, I will try to solve these 3 problems so you can compare your solution with mine, which actually these are very interesting ones. Right, I'm gonna stop sharing here. Okay, so I'm just gonna try one more time. Perhaps now it's a little bit more clear to show the bar. All right, so this is the bar here. And if I apply a lateral load, so here is the lateral vibration. It's obvious through the eyes, and it actually vibrates for a maybe longer period of time. All right, so that's one mode. Perhaps you can see the standing wave. If I stay a little bit further away, maybe it's a little bit more clear. Now I kill them, right? But longitudinal vibration, we should not be able to see it, but hopefully we should be able to hear it. If, of course, if I apply rosin on it, maybe it sounds better. I just use actually a coin. I'm just gonna try. Now it seems it's loud and clear, hopefully. So, so don't forget then the longitudinal vibration, you cannot see it because it's molecule level. It moves like along the axis of the bar. We may be able to hear it. Or maybe if I put a sensitive accelerometer at here, I can measure the vibration, longitudinal vibration. All right. Thank you very much for listening, and stay tuned for the next video where I solve the 3 practice problems that I just showed you.